Ladies and gentlemen, welcome to the next session of our introduction to cellular automata. In this session we look into the transformation or the extension of our 2D cellular automata to a 3D cellular automata. This means we not only want to extrude our cells as we've seen it in the last session, now we want to apply the transformation rules to a neighborhood that extends to a three-dimensional grid. So we want to consider also cells below a cell or above a cell. Therefore, we start from what we've done so far. I've provided you an extended definition of the cellular automata underline 03, underline 3D. That's the name of the definition that you please open now. In this definition, if we zoom out, we see the initialization. This remains the same. Also the 2D cellular automata, we don't change here anything. We run the 2D cellular automata and receive, for example, this result. And now you see this part below the old definition, where we have the 2D to 3D cellular automata loop. Here we start from the results from our 2D automata and transfer this to the status or the initialization of a 3D cellular automata. Therefore, we look into the initialization, which is changed a little bit. What you can see is we read the cells again. This is the same input as we know, but here we added the states 2D. So here we input the results from the 2D cellular automata into our 3D cellular automata, and we define the number of the levels, so the number of floors or the y coordinates of our grid of our cellular automata, so the third dimension, how many levels we want to have. In this case we choose 4, and we see they are read into our script, and here it's quite short. What we do is we just test if there are any inputs from our 2D cellular automata, and if yes, we just copy the states of the 2D cellular automata into the states of the 3D cellular automata. So here we see once again a list of integer values, and this line copies, or it initializes the list for state 3D based on the 2D states. And so this means we filled the ground level, and in this for loop, or in the nested for loops, here you see we repeat this until our number of level is reached, and we start from 1 because the ground level is already filled by this initialization part. And here, starting from 1, so from the first floor, we just fill the grid with empty cells. So state 1 is added to the list. That's very simple, and we return the states 3D as a new initialization. This means, what have we done? Let's see if we can see this correctly in the preview. No, cannot, because we need to send states here. So that's our initialization. We've just taken the results from the 2D automata as the initialization of the 3D automata. Okay. Also the rest remains the same. There is not much changed. Here we just copied the same anemone loop, everything familiar. In the visualization I've used the part that was used for the extrusion of the 2D automata. We just use a different cull list, where we read the states of our cellular automata as a cull pattern, and the list of all our cells in this example. So we have a 20 by 20 2D grid in 4 levels. So these are 1600 cells that we have now. And the call pattern will then just removes the empty cells in 3D. And the rest is then the same. We extrude the 2D rectangles and create the preview out of it with a little gap between the stories or the floors to visualize a kind of a scaling idea. Okay, but the main part once again is in the CA script. Please open this script window. And here you see also there's not much of a change. The main thing that changed is that the states array now becomes a 3-dimensional array. So the dimensions of the array you can see by the number of semicolons that we have here. So this means we have 3 dimensions that we could fit into it. So imagine there would be numbers 1, 2, 3 places we have. And the limbo word is also extended to 3-dimensional array. In the for loops, we added one for loop for the number of floors. I used the iterator variable f that iterates through all floors. I start with floor number 1 because I don't want to change the result from the 2D automata. Means I don't want to change the ground floor. This will be kept always the same. But from floor number 1 we start with the real 3D roots. The rest is the same as you know it from the 2D automata, but as we may expect, what we change is the cells that we consider as neighbors. The neighborhood is extended now to 3 dimensions as well. So our voting rule, the neighborhood that we consider, is changed. That's this part of our code. Here I have not only changed the dimensions, but also from the Moore neighborhood to a von Neumann neighborhood, as written in the title. And here we start again with the 2 dimensions. So I ask first for the neighbors in the same level. And the von Neumann neighborhood, you may remember, let's make a screenshot again to explain the von Neumann neighborhood as a reminder. In this case, we don't use the 8 neighboring cells, we use the 4 direct neighbors only. So if we consider this cell, then the neighborhood of the von Neumann is this one. So I would ask this, and this cell, and here we would count only 1 as state 1, and these have the state 0. Here I would have the status 1, but this will be removed again because that's the considered cell. Let's look into the code. What I do here, I iterate from -1 to 1. This is the Moore neighborhood, but I only count the state if I am either in L equals 0, so my rows, or my columns equals to 0. If you remember the screenshot, let's erase this. Here I consider the full neighborhood with my 2 for loops, but I only count it if either L means either the columns are 0 or the rows are 0. So I count only these cells. That's done with these 2 if conditions, respectively the if and the else if either L or M is 0. Means it's in the center of our grid. Then I sum up again the states. And finally, as you know it from our last example, here I subtract the own state of the cell. And the 3D part is only, here I only consider the cell below the one that I've considered. So I extend the von Neumann neighborhood only to the bottom, only below the current cell that I consider. And therefore I only need one line of code. That's f minus 1. That's my floor level minus 1, starting with 1. And x and y, it's the address of the current cell. Here I don't need to check the border because I know I'm above level 1 and I only go down one step. And then I store the result in my limbo world, which has now 3 addresses for 3 dimensions. And the rest is once again the same, only that I go through all 3 dimensions of my limbo world, starting from floor 1, and again asking all the cells in each level, and applying the exact same transformation rules or counting rules to change the states of the cellular automata. And all the rest of the code is exactly the same. It's just that I added 1 dimension to the cellular automata. The rules are the same, that decides how to change the status. And the only thing that I've changed is the definition of the neighborhood. Now let's look at the results. Here I recommend you to use a few steps for the beginning. For example, 5. And to move the window to the left side. Now the automata is running. And here, you see, for the visualization, I changed the way how I wired it. Now I have to restart the automata, and what you should see now is the development of the automata in 3 dimensions. So here you see there are also cells added in different locations of the 3D grid, not only extending the 2D footprint, but having a more complex pattern that I generate with the 3D automata. It's harder to control, and also the rules, to define the rules, it's not that trivial as in 2D, so now it becomes really more difficult to understand and to imagine what result you will create with which rule. Here the 2D pattern is still somehow there, but also changed a little bit. What happens now? Previewing anymore. Anyway, right. That's basically the idea of the extended 2D automata. You see, I provided you here only one rule. You are absolutely free to change the states of the automata and also the decision rules once again, and which neighbors you consider. You can, of course, also consider the Moore neighborhood for the 3-dimensional automata. The code is also in there. The old one for the Moore neighborhood, you just need to ensure that you add the floors to count in this neighborhood level. And you can also experiment with new rules to generate new patterns. What you can do as well, I want to show you here another possibility. You are not restricted to this vertical level. I've already mentioned you are free in defining how you, or to which area you want to apply your automata. Therefore, I prepared here another input. Just reduce the size of the automata because my computer gets slow. What I've mentioned is that you can also use another area for the initialization of your automata. In this case, I want to show you how you can use vertical grid. Therefore, I prepared just a different rectangle, which I've drawn on the front view. And here you see I added my cellular automata just by selecting a different shape as a boundary for my grid tiles. The rest works exactly as we used to see it. And the only thing I need to change is if I add the 3D automata. So this is now the 2D, there is no problem. The filled cells are applied to the second dimension. But what we need to look at is now the extrusion of the objects. Here you see something is not correctly extruded and moved. Therefore, please look at the visualization part of the 3D automata. Here we move the cells to in the Z direction, or we have the unit vector in Z direction. We just need a unit vector in the Y direction and exchange the Z to the Y direction, extruding it to the horizontal axis. So now we move the rectangles, respectively the surfaces, into the Y direction, and if we extrude it also in this direction, then you see you receive the correct three-dimensional cellular automata in a different direction. And if we run this now 5 iterations, it also works in a non-horizontal way. The logic is the same. Also the result, it's just applied, for example, to a facade, where you can create facade patterns or other applications for your cellular automata. Well, with this, I think now you have seen a lot of entry points. I hope you already got some ideas how to apply the cellular automata, or what to do with it, how to explore with it to find your own applications. I hope you enjoy playing around with it, and good luck with changing the C# code.